Welcome to Spring LIB.
For this problem on the topic of electromagnetic induction, we are given a circuit as shown in the figure, and we are also given the capacitance and the voltage to which it is initially charged. We have a resistor R0 with a given resistance, and we know at time t is equal to 0, the switch is closed. The small circuit in the diagram is not connected to the large one at all. And we know for the small circuit the resistance per meter and the number of loops for the circuit. Now the large circuit is a rectangle, and the small one has given dimensions. Now, if both circuits are held stationary and only the wire nearest the small circuit produces an appreciable magnetic field, we are asked to calculate the current in the large circuit 200 microseconds after the switch is closed, the current in the small circuit at the same time, the direction of the current in the small circuit, and then we are asked to justify why we can ignore the magnetic field from all the wires of the large circuit except for the closest one. Now, the current in a discharging RC circuit, I is equal to V0 over R e to the minus t over RC, where V0 is the initial voltage across the capacitor. Now, for the small loop, the resistance is the number of loops, 25 times 0.6 meters times 1 ohm per meter, which gives us 15 ohms. So let's begin to solve the problem. So in part A, we know the large circuit is an RC circuit, and an RC circuit has a time constant τ, which is equal to R times C. And this is equal to a resistance which is given as 10 ohms times the capacitance of 20 microfarads, or 20 times 10 to the minus 6 farads, which gives us a time constant of 200 microseconds. So the current is as a function of time, I is equal to 100 volts divided by 10 ohms to the times e to the minus t over 200 microseconds, t over τ. So if we let t be 200 microseconds, we get the current I when t is equal to 200 microseconds to be 10 amperes times e to the minus 1. And so this current is 3.7 amperes. So that's the current in the large circuit at a time of 200 microseconds. Now we want to calculate the same for the small circuit. So if we assume that only the long wire nearest the loop produces a magnetic flux through the small loop, and we refer to our hint, we get the magnetic flux through the small loop phi b to be the integral from C to C plus A of mu naught I b over 2 pi r dr. And all of these are constants, so they come out of the integral, and if we solve this, we get this to be mu naught I times b over 2 pi times the integral of 1 over r dr, which becomes the natural log of 1 plus a over c. So therefore, the EMF induced in the small loop at t is equal to 200 microseconds is epsilon, which is minus n times the rate of change of flux, d phi b dt. And we can write this as minus n times mu naught times b over 2 pi times the natural log of 1 plus a over c times the only thing that changes with time here is the current, so di dt. Now we can substitute our values into this and we get this to be minus, and n is 25 turns, times mu naught we know is 4 pi times 10 to the minus 7 in SI units, which is Weber per ampere meter squared. We'll suppress the units here, times B, which we are given to be 0.2 meters divided by 2 pi times the natural log of 1 plus a over c, which is the natural log of 3, multiplied by minus 3.7 amperes in a time of 200 microseconds, so 200 times 10 to the minus 6 in seconds. Since all our values are in SI units, we get the EMF epsilon, the induced EMF in SI units, to be positive 20 millivolts. So if we have the EMF, we can find the induced current in the small loop. So the induced current in the small loop we'll call I prime. I prime is equal to epsilon over R. And we've already found the resistance of the small loop from above. So this is 20 millivolts over the resistance of 15 ohms, which gives us the current induced in the small loop to be 1.33 milliamperes. So now we have the current in the large loop as well as the current induced in the small loop. Now we want to find the direction of the current in the small circuit. Now the magnetic field from the large loop is directed out of the page within the small loop. So the induced current in the smaller loop will act to oppose the decrease in flux from the large loop, and so the induced current flows counterclockwise. And finally, for part D, we want to know why we can ignore the magnetic field from all of the other wires of the large circuit besides the closest one. And the answer to this is that these 3 wires in the large loop are too far away to make a significant contribution to the flux in the small loop. And we can see this by comparing the distance c to the dimensions of the large loop.